confiance, amour, solo, Gao, l'Algérie, Tunisie, Italie, y a pas de problème, j'aime au Manhattan, fast food, Dakar, Sénégal, cinéma, le Paris, ascenseur pour le ghetto, il est minuit à Tokyo, il est 5 heures au Mali, quelle heure est-il au paradis? Il est minuit à Tokyo, il est 5 heures au Mali, quelle heure est-il au paradis? C'est au Manhattan, fast food, Dakar, Sénégal, la grand-mère à l'hôpital Dantec, tout va bien, Kairek, moi ici, toi là-bas, le visa au consulat numéro 39, y'attend, à l'état civil, déjà l'an 2000, déjà 2000 ans, au Manhattan, fast food, Dakar, Sénégal, cinéma, le Paris, cinéma, le Paris, il est minuit à Tokyo, il est 5 heures au Mali, quelle heure est-il au paradis? Il est minuit à Tokyo, il est 5 heures au Mali, quelle heure est-il au paradis? Dakar, Bamako, Rio de Janeiro, où est le problème, où est la frontière? Entre les murs, se faufiler dans l'ascenseur, ascenseur pour le ghetto, au Manhattan, fast food, Dakar, Sénégal, cinéma, le Paris, cinéma, le Paris.
Hi, everyone. I hope you can hear me. Sorry for the delay. There's a bit of technical hiccups as it has been recording with this thing of multi-streaming. So I hope you are having a great Friday. Welcome, everyone, from the founding members on Substack and QF Academy on the private mode. Remember, if you are on the private mode, any messages or comments you make will stay private to you, but I can see them. Okay. The other ones on the public channels, I'm afraid, I'm sorry, you don't have this luxury of privacy. So yeah. So welcome to our second session of Field's Happy Hour. So the idea is basically to celebrate this year's Field Medal winners. Previously, during the first session, we covered our first field medalist, Yudeng, which is now available on our Substack. So please feel free to go on our Substack and check it out. I think you will like it, and well, I hope you will like it, so you can learn about Yudeng's contribution to mathematical physics, in particular to partial differential equations. Today we are in a completely new field. In fact, I have to apologize because we need to do a little bit of an adjustment of the program, because I had invited a friend of the community who is an expert in arithmetic algebraic geometry, who was meant to walk us through this today's field medalist's work. Unfortunately, because of a family issue with the baby, he couldn't make it. So I'm afraid we have to, go without him. But he promised to come back again to give a webinar about Jacob Tsimerman's work. So yeah, I'm really sorry for this. So I hope you will like my improvise. We'll still go ahead. But yeah, I'm really gutted. Yeah, but it is what it is. These things happen. Family comes first. So yeah. So I hope you are having a great Friday for joining us at this time, especially the ones in the United States. Where are you guys tuning in from? See, look at the chat. San Francisco Bay. Okay. Where else? Mumbai. Namaste. That's all I can say in Hindu. I hope I said it correctly. Chile, Santiago. Wow. I mean, I'm not surprised because, in QF, we are a global community as always. I always say this, when we have live events, because, I'm aware that we have community members spread across the globe. Where else? Glasgow. Okay, that's closer to us, to our company. We are based in the UK, in Liverpool. Yeah, we are in the northwest. You are a little bit up north. Where else? Helsinki. Okay. Okay, yeah, well, thank you so much for for taking your time to join us. And yeah, I hope you enjoyed the session. And I'm sorry again for the improvisation that we have to make, because unfortunately our guest couldn't join. So yeah, so let me just what I will do. So first of all, don't forget to go and check out this on our Substack, the first field medalist that we covered, Yudeng. So today we are covering Jacob Tsimerman. So he's our second field medalist we are covering today. So I'll just give a brief bio from what I understand. I took some notes, so I will be reading from my notes, because as you can imagine, I cannot memorize anything to do with the thing, especially bios. It's too long. But from what I understand, Jacob Tsimerman was born in Kazan, I believe that's in Russia, in 1988. His family later moved to Israel and then eventually to Toronto. And interestingly, he actually represented Canada twice at the International Mathematical Olympiad, winning gold medals in 2003 and 2004, with a perfect score in 2004. Wow. At 16, when he was 16 years old, he entered the University of Toronto and completed his undergraduate degrees in mathematics in 2 years. Wow, this is impressive. I believe actually in this, he might have skipped high school. This is just to show you how talented he is. So he then went to Princeton for his PhD under a well-known mathematician in the mathematical community, Peter Sarnak, where he graduated in 2011, according to my notes. During his PhD, Tsimerman started to work on problems connected with the André Oort conjecture, including questions about Galois orbits of special points and their intersection with ideas being developed by Jonathan Pila. After Princeton, he became a junior fellow at Harvard's Society of Fellows before returning to the University of Toronto in 2014. So yeah, he's like similar, more or less, not far in terms of trajectory with Udeng, but you can already see in the early teenage years he was already like showing signs of mathematical talent, really. So his research really spans the field of number theory, arithmetic geometry, algebraic geometry, and Hodge theory. He made major contributions to the proof of André Oort conjecture, which is one of the things that he will be one of the main factors for winning the field medals this year. He also helped establish this thing, well, let's call it a framework because we are a software-driven community, called o-minimality, as a powerful tool in arithmetic geometry, and later worked on stuff like period maps, functional transcendence, o-minimal, Gaga, and Griffin's conjecture. So yeah, he's really like you can see he's already like very heavyweight thing. So very impressive CV. It's pity our arithmetic algebraic geometry friend who was meant to join is not joining, but yeah, let's just before we proceed, this is something that I thought you might want to know, is that Jacob Tsimerman's work, in terms of like being able to understand the nature of his work, you really need very, very, very advanced, in particular, very abstract mathematics. This is in contrast to say our first field medalist, Udeng, whose primary work is really around partial differential equations. This is something that we are all familiar with, right? If you do engineering or mathematics, you generally have PDEs. So Udeng's work is much more, I would say, in terms of accessibility, in terms of barrier, there is less to compare to Jacob Tsimerman, because Jacob Tsimerman is really working in the really, really, really like very, very deep and advanced fields of mathematics. And even for mathematicians, I think to have a good overview of his work, you really need like, to have some familiarity with the stuff like algebraic geometry, arithmetic geometry, number theory, complex geometry, Hodge theory for sure. In my case, just a disclaimer, I'm not really familiar because the type of these fields of mathematics are not really the things that I'm most familiar with, really. So I'm familiar with them because they exist, and I also admire some mathematicians who worked in these things, people like Grothendieck, we will talk about him towards the end, and also other mathematicians that I am aware of, people like, of course, one of my favorites, Jean-Pierre Serre, Pierre Deline, all these giants, and also I believe this year's Abel Prize winner, Faltings, So, to understand the work of Jacob Tsimerman, really need to be able to feel comfortable with this, to have some sort of a background of these fields that I just mentioned. Now, because I don't want to discourage you from being curious about abstract maths, because this is the essence of our community, right? We want to make abstract maths accessible in these type of things. You hear us say. So, in particular for our community members, who are just getting into mathematics, or also lifelong learners within the community. So what I did was to get some resources that I myself went through with, in order to try to digest a little bit. I won't even dare to say understand, but to try to get a little bit of the essence of Jacob Tsimerman's work. So I will share that with you, so that you can, when you watch one of the talks that I will share in this session, you can go back and reference to those resources in order to be able to try to follow something. Okay, this is exactly what I did. I went through those books, graduate. Some of them are like introductory books, as you will see, just to refresh myself. There are some things that I already knew, or be it have some knowledge of, but I really had to work deep in going through the thing in order to follow, to get some toolkits, prerequisite that I needed to have a little bit of a idea about his work. And I must say that I was really impressed, especially with his creativity. I'll comment on this as we go along. So let me just pull up the slides for the resources that I definitely recommend you if you really want to get some flavor of his work. Okay, so just bear with me. See, now I need to find the share button. Oh, okay. So we have to do it the hard way. Just give me a second. I wasn't expecting this. For some reason, I have some issues with the thing, with the system. In fact, let's, instead of doing this, just to give me time to organize myself to share with you, what I will do, I will play a clip of a very accessible intro to his work, and then we'll come back to the background that I think you should have before we watch together the other talk, a laudation talk in his honor. Okay, so let's see. Let's see if it plays. I hope you can hear. Let's see. I'll go maximum so you can see. And then I will disappear just to enable you to go to watch this in peace. I'm sorry. Sorry for this. Seems like someone was just pinging me on the chat that the screen share wasn't sharing. Let's see. Sorry for this. So we'll replay again. Let's see. Let's see. Just give me a second. This is the thing with the sharing things cross platform. Okay, I hope you can see this. Let's see if I go full screen, whether you can still see. Okay, so I'll let you watch this. I will just turn off my thing so you don't get distracted with me. But yeah, enjoy this brief overview, and then we'll come back to the next segment with the recommendation about the resources that I think you need in order to get the essence of his work. And then at the end, I will have a comment about what I think, what I could understand from his contribution. And finally, with this thing about the impact of Alexander Grothendieck to Tsimerman's work. Okay, so.
No, you should have said the actual word nothing, then there was going to be a funny joke.
We're thinking about maybe considering you for a paid position.
Paid with like the money you have in your wallet?
I really like improv. What I really like about it is how off the cuff it is, how you have to make decisions quickly. It's so different to how I live most of my life, and especially with math, how slow it is, how careful it is, every little piece has to be checked. Most of my work is entirely in my head. There's no experiment, there's no lab, there's just ideas. It's just you and the problem. We have these intuitions that let us see these patterns. Often you see these connections and you have no idea where they're coming from, sort of how to build a bridge from one side to the other. I'm a professor of mathematics at the University of Toronto, and this year I'm the distinguished visiting professor at the Institute for Advanced Study. We're running a special year here on o-minimality and Hodge theory. I remember the first math puzzle I heard from my grandpa. It was a little puzzle about a toaster. If you have a toaster, but it's broken, so both slots only toast one side of the bread, and you have 3 pieces of bread that you want to fully toast both sides of, how many times must you use the toaster? It was this question that I could understand, but I couldn't answer. And then I heard the answer and I was like, that's beautiful. And I was basically hooked. I think from then on, I did math with my grandpa, then my mom. Every chance I got to engage with math, it became my recreation time. I really fell in love with competitive math, not even so much between me and other people, but between me and the problem. I think one of the main skills, both in contest math and research math, is the ability to stay engaged, to try and stay engaged with the puzzle, with the problem, even when you don't know what to do next. It can be easy, I think, and tempting in those moments to sort of just give up. And I think contest math really taught me not to do that. Kablamo!
Oh!
You can definitely take it out.
But if it falls.
Okay, that's my fault. That it's secretly my fault. That wasn't the way. We're competitive when we play board games, for sure. We try to win. Playing hard and fighting hard is part of the fun. My wife's name's Pia. She's great. We do all sorts of things together. All my friends love her. We got married last year, and then we had a daughter this past December. These days, we mostly spend our time with our daughter, trying to navigate being new parents together. It's very hard to know as a mathematician what you're going to figure out next. It's especially hard when you're seeing all of these like celebrations of success, that you don't see all the mountains of failure. I studied the application of o-minimality to algebraic geometry. So in algebraic geometry, we study shapes determined by polynomial equations, lines, circles, parabolas, very rigid structures. There's this much bigger world of analysis where there's a lot more functions and freedom. And one way of studying algebraic geometry is to dip into analysis. So take, for example, an elliptic curve. Its complex points make a one-hole donut with a complex structure. If you unwrap it, you get a parallelogram, and the ratio between the sides is a complex number. So this is an analytic function on the moduli space of elliptic curves. And if you go to degree 5, you get a two-hole donut, which unfolds into a hyperbolic octagon. This is the beginning of Hodge theory, which uses period integrals as a way of studying these algebraic objects. A difficulty is that analysis contains very wild and unpredictable functions and shapes, things like essential singularities and natural boundaries. So working there requires you to give up all this control. Now, o-minimality is a great framework for functions that don't exhibit this behavior, and it's sometimes called tame geometry. The key idea is we start with dimension 1, which is a line, and we only allow finite unions of points and intervals. In every other dimension, we allow only shapes such that no matter how we play them against each other, intersection, projection, etc., once you end up back in dimension 1, you again only get those finitely many points and intervals. So for example, the graph of the sine function is not allowed because of its oscillatory nature. So what we did is we defined this intermediate world of definable analytic geometry and showed that Hodge theory lives there. And this allowed us to prove Griffith's conjectures on algebraicity and semi-ampleness. There's this like permanent feeling of being stuck when you're doing math. You're constantly trying to get from A to B. It can take a very long time and a lot of breakthroughs to see that bridge. There's nothing really around to help you except for other people who maybe have other good ideas. Just to succeed at anything, you have to collaborate because math is so big. Almost all mathematicians now don't work alone. It's more fun when you get to sort of share your burden. One of my favorite ways of working is to call up somebody, a collaborator, and just go on like a 2-3 hour walk, throw ideas around. Through working together, our islands overlap more and more. I think a lot more of my life exists in community with other people now.
En fait, la communauté vous fait avancer. Explorez votre histoire.
The advertisement, this is the downside of doing things from YouTube. Yeah, so sorry for the technical issues that we had while I was initially trying to share, but it seems like it wasn't sharing. So yeah, let's see. Okay, yeah, so yeah, it stopped. So yeah, so I hope this is a very nice, I would say, accessible introduction to his, I won't say to his work, but just to give you some a superficial overview, you know, in the most simplest way possible. Because as I said, to really understand his work, or at least have a little bit from a technical point of view, you know, you need to have, you know, a good background in stuff like algebraic geometry, arithmetic geometry, number theory, complex geometry, Hodge theory, and so on. In fact, this is actually one of the things that makes him very special, because his work is at the intersection of all these fields. And very, for some of you outside mathematics, you might have this, I would say, how would I put it in a diplomatic way? You might have this naive sense that all mathematicians are the same. You know, someone is a mathematician, well, they must know everything about maths. But that's not the case. Mathematics has become very specialized in such a way that, it's very hard sometimes, for two mathematicians working in completely two different fields to, communicate with each other, or let alone to understand each other. In fact, there has been a lot of efforts in trying to using a bit of inspiration from physics, trying to build some sort of a framework that connects different branches of mathematics, through programs like Langland's program. So if you are coming from physics background, this could be like, in a naive sense, some sort of a grand unified theory for mathematics, okay? Don't take it too seriously. It's just some, very lightweight analogy. So as I was saying, what I did, for me to try to get a glimpse, as I said, I'm not very familiar with these corners of mathematics. Okay, so what I did was to, with the help of our friend who is an arithmetic algebraic geometer, who was meant to be on stage with me today to walk us through his work, but unfortunately, because of family reasons, if you are just joining, he couldn't attend, but he will do a seminar after for the community. So in the meantime, what I did myself independently over the past 2 weeks, as I was waiting for this event to be scheduled, was to gather some resources and use those resources as I was watching the technical talks as a reference for me to try to understand something, about what Jacob Tsimerman his work is about. So I will share some resources with you that was, I would say, very helpful to me, and I hope they might be helpful to you if you are, into the actually, trying to have some sort of understanding beyond what you just saw in this like very elementary introduction to try to convey his work. So let me pull up a slide just to share with you. I hope you can see this. Well, I've now disappeared. Yeah. Yeah, so this is the thing. This is definitely a must because his work is basically at the intersection of algebraic geometry as well. So you definitely need to have some idea about algebraic geometry. So in fact, I myself, I was looking at this book as I was watching the lectures, going back again, even to looking at the basics, what's well, I mean, I already knew in a basic sense, what affine and projective varieties were, but beyond that, I had to really, consult resources like this on the algebraic geometry side. So take a note of this. This is the first reference that I think you need, or it will at least be helpful for you. The second reference is, let's see, this one here on abelian, basically on diophantic geometry. So, you will be able to understand basic stuff like abelian varieties, varieties, points, on algebraic varieties, all these other, important toolkits, notions that you need in order to try to make sense while you are watching the technical talks about Jacob's work. Yeah, so this is another great reference that I think you should consider. The third reference is this one on complex abelian varieties. Okay, so you will look at stuff like complex stories, abelian varieties over complex fields, right? So you will really look at, and you also have some a bit of contact here with the complex geometry, basically, of course, aspect of Jacob's work, in order to, you will see in a minute, the other technical talk that I will share for his laudation, to try to put all the pieces together to understand what the professor is saying about Jacob's work. And also Jacob's has his own presentation, but that's too long. I won't play it here. So this is definitely a reference that I recommend you. I think I have more references. Let's see. The other one is an introduction to basically moduli spaces, let's say. Okay, understand what a moduli or moduli, some people, depending on how you pronounce it. So this is very important because they play a role, as you will see when I start to play the second clip. So go and take a look at this. In fact, I would say in terms of moduli spaces, I would say most of you, especially those of you coming from quantum formalism, our academy, I would claim that you already dealing with moduli spaces without knowing. And this is because manifolds, manifolds, they are actually moduli spaces as well. So you are not aware of the moduli space structure, right? Because you haven't learned it. But in a sense, you're already dealing with them without knowing, okay? Without knowing what it is. So this book is a very good reference. I found it very useful, at least in my thing, trying to piece together while I was checking the technical talks about Tsimerman's work. This one also is very important because this framework, this o-minimality framework, is very important in his work. And this book is basically, a right fit for you to try to understand what an o-minimal structure is. So go and look at this as well. So I was scrambling around with all the resources that I already shared with you, plus this, to try to fit together, to try. And even then, I think, I don't think I even have like 1% understanding of his work, to be honest. But I think I could follow enough to really see that, the importance of the work, So yeah, so go and play around with these resources. Actually, I think there is another one actually also, which is very useful, which is this thing by by Shimura varieties and moduli, or moduli, whatever you want to pronounce it, by J.S. Milne. By the way, J.S. Milne, this website, you should go and visit it. It's a gold mine for mathematics. I remember, more than 20 years ago when I was in my students' days, this was a place that even my professors used to go. So he's got a lot of other interesting resources. I remember my first, one of the few free PDFs that I got on Galois theory was through J.S. Milne. So it's a very great resource for finding things about this. So go and check this. After you do this, what I recommend you is to go, and as you are watching, it's a slow process. It's painful. Okay, as you are watching the technical talk, for example, the one that I will share, or even Jacob's presentation, you can go back to those resources and try to take notes and these things to try to put the pieces together so you can follow. This is what I did, and it was like the hard way, but at least I was very happy that I could follow parts of the presentations about his work, and I'm very confident that I have some understanding about his work, not as an expert, but a little bit more than the superficial thing that you saw in the accessible video that I gave you before. So yeah, so I hope you enjoy this. Now let me go and try to pull the other resource, the other play list that I think you should definitely look at. Just give me a second. I'll go around. In the meantime, feel free to post your messages on the chat, and you can share anything, any comments. I will go and take a look at it. So let me just find it. I'm now on the playlist of because I closed the tab by accident. I lost the playlist, so I need to find it now in the it's like needle in a haystack, right? Where is this? I need to try to find it within the Simon Foundation YouTube. Let's see, give me a second. I think it's this one. Voila, let's see. I'll just skip to exactly. Okay, yeah. I'm just skipping to the right place so I can play this, and then I'll come back again. Okay, so it's here. Sorry for this. Just give me a second for me to share the screen again. As I said, this was improvised because we meant to have our friend from arithmetic algebraic geometry to give you an overview because he's an expert in topics pertinent to Jacob's work. But unfortunately, last minute he couldn't join, so we have to improvise it this way. Let's see. So I will stop sharing this, and I will share the other screen. We'll watch it together. Or I might disappear for a bit. Let's see. I hope you can see this. Yeah, on the chat, can you see this? Okay, so I'll play. Maybe I'll put
major contributions across a wide swathe of fields, including arithmetic geometry, Hodge
I think
theory,
it's actually, it didn't start. Let me go back, skip to start from
Thank you very much, yes. So
yeah,
Jonathan,
so this is better.
Floor is yours.
Yeah. Watch it together, okay? I will be taking notes as well, so I can make my comments.
So, hi everyone. It's my honor to say some words about the work of Jacob Tsimerman. Jacob is a brilliant mathematician who has made major contributions across a wide swathe of fields, including arithmetic geometry, Hodge theory, algebraic geometry, and number theory. This talk is about the work of Jacob and not about working with Jacob, but I just want to say what a pleasure and privilege it has been for me to work with Jacob for 15 years now. And beyond his brilliance, he is a wonderful collaborator, and working together has been immensely enjoyable.
Sorry, thank you, Claudia. Sorry for this. I mean, this is why it's a live session, so, it seems like I was muted before. Can you hear me now? I'll repeat this again. I'll go over it again. In the recording, we'll clean up all this. Don't worry. Can you hear me now? Can you post on the chat? Just let me know. in any case, I will say what I was saying when I was muted after. So I'll just play it so you can.
For lack of time, I will address only Jacob's contributions around the André Oort conjecture and in Hodge theory. Oh, right. So to introduce the André Oort conjecture, I will set the scene with Diophantine geometry, which in the first instance studies the rational points, that is, points with rational coordinates on an algebraic variety, which is a set in complex space defined by polynomial equations. There are many questions one can ask. A convenient general question for my purposes is, which algebraic varieties can have a Zariski-dense set of rational points? The Zariski density means that there is no additional algebraic equation that captures all of the rational points. If there were, we could move our investigation, we could impose that extra condition and move to some smaller algebraic subvariety. When V, the variety is one-dimensional, a complex curve, Zariski density of rational points is the same as having infinitely many of them. And the answer to the question, famously conjectured by Mordell in 1922, was proved by Faltings in 1983. And the answer is that on a curve of genus 2 or higher, there can be only finitely many rational points. So they're simply not, they can't be Zariski dense. Faltings went on to answer the same question for arbitrary subvarieties of abelian varieties. Only cosets of abelian subvarieties by rational points could have a Zariski-dense set of rational points. Now, an abelian variety is a group variety, and it has an abundance of torsion points, which are points of finite order in the group. And now one can ask, which subvarieties of an abelian variety can have a Zariski-dense set of torsion points? Raynaud proved the theorem conjectured by Manin and Mumford. Only cosets of abelian subvarieties by torsion points have this. Now, for general varieties of dimension 2 or more, the original question about Zariski density of rational points is wide open. Now, the André Oort conjecture is an analog of the Manin-Mumford conjecture for Shimura varieties and their special points. A Shimura variety is a very particular kind of algebraic variety. It's a moduli space parameterizing suitable objects. For example, it might parameterize abelian varieties of some suitable dimensions. If positive dimensional, it has an abundance of so-called special points, and these are the points that correspond to the suitable objects with maximal extra symmetries. They are algebraic points with rich arithmetic properties, and one can ask, which subvarieties of a Shimura variety can have a Zariski-dense set of special points? The André Oort conjecture proposes the answer only on special subvarieties, which are essentially Shimura subvarieties, and which do indeed have Zariski-dense special points. André himself proved the first non-trivial case in 1998, but subsequent results were conditional. They led to a full proof conditional on the generalized Riemann hypothesis by Klingler, Ulmo, and Yafayev. The point counting strategy employs rational point counting results for definable sets in o-minimal structures. And so it relies heavily on ideas from model theory, which I won't go into. Jacob's, the movie, had a beautiful pictorial description of o-minimality, and which we'll come back to later. But the key point about this strategy is that it reduces the André Oort conjecture for a given Shimura variety to 4 discrete ingredients. And I will focus on the geometric ingredient and the arithmetic ingredient and Jacob's contributions to them. By the work of many people, spearheaded by Jacob, this led to a full unconditional resolution of the André Oort conjecture in the period 2011 to 21. Now, the geometric ingredient concerns the uniformizing map of a Shimura variety. A Shimura variety is uniformized by a Hermitian symmetric domain by a map which is invariant under the discrete action of an arithmetic group. The simplest example of this is the J function, the modular function, which maps the complex upper half plane to the complex line. A Shimura variety known as the modular curve, which parameterizes elliptic curves up to isomorphism over the complex numbers, and the Cartesian powers of that setup. The paradigm example is the uniformization of Siegel modular varieties, which parameterize abelian varieties of a given dimension by the Siegel upper half space by the map given by automorphic functions. But a prototype example for what I want to describe, though it's not a Shimura variety, is the complex exponential map and its Cartesian powers. The functions giving these maps are non-algebraic. They're transcendental maps, but we need to know that they strongly avoid everything algebraic. And in particular, what we need to know is that the graph of these maps intersect algebraic subvarieties only in the expected dimension, never higher, except for clearly delineated exceptions, which, of course, are connected to the special subvarieties. The prototype result is known as Ax-Shanwell, and it's the result of this form for the exponential function and its Cartesian powers. And this theorem, which I'm not going to state, I'm simply going to say that it is a functional version of Shanwell's conjecture on the transcendence of the values of the exponential function. And that conjecture is written on the slide. And those numbers, too, are conjectured to be as transcendental as possible, given the functional equation satisfied by the exponential function. And I want to say also that only a special case of Ax-Shanwell is needed to prove André Oort, but the full statement is the natural one and useful in generalizations. These results were established over the period in increasing generality by Jacob and collaborators and others, culminating in the proof of a functional version of André's generalized Grothendieck period conjecture by Baker and Tsimerman. The period conjecture asserts that the integrals, it's again a conjecture about numbers. It asserts that the numbers given as the integrals of algebraic functions over semi-algebraic domains, things like the area of a circle, are as transcendental as possible. And on this conjecture, see the beautiful article Periods by Kontsevich and Zagier. André's version of the conjecture includes Shanwell's conjecture as well. And the Baker-Tsimerman functional result includes all the previous formulations in Shimura and Hodge settings. So now I want to switch to the arithmetic ingredient that is needed, and that is that the Galois orbit of a special point is large. So I've described this in the sentence in purple on the slide, and then also a version with quantifiers for each Shimura variety. There exist these two constants, and so on. So the Galois orbit is supposed to be large relative to the discriminant of the special point, and that means at least some positive, fixed positive power. And the prototype for this result is a famous, a very classical result of Landau and Siegel from the 30s, generalized by Brouwer, on the size of the class number of an imaginary quadratic number field. So there on the slide is the prototype result. So for the J function, the Galois orbit of a special point corresponding to the ring of integers in an imaginary quadratic field is in bijection with the class group of the field. And the classical lower bound for the class number, which is the size of the class group, in terms of the discriminant of the field, which is the discriminant of the special point in this case, is exactly the shape of the bound needed. So there on the slide you have, well, the Brouwer, the Landau-Siegel class number estimate. These results were established in three waves. First, Jacob proved them directly for the Siegel modular varieties up to dimension 6. That dimension is the dimension of the abelian varieties being parameterized in his paper, Brouwer-Siegel for arithmetic tori. The proof for all Siegel modular varieties went a different way. It went via something called the Faltings-height of a special point. Using the isogeny estimates of Masse-Wustholz, one can show that if the height is small relative to this discriminant, meaning discriminant negligible, then the Galois orbit is large. This height is explicitly predicted by a conjecture of Kolmez, which is still open, but average version of it was proved by two groups independently in 2021, and the average version somehow sufficed to conclude this pathway. Now, the third step was the general Shimura variety, and there one does not have isogeny estimates, nor a Faltings height, nor a Kolmez conjecture. But here, a sharp point counting result due to Binyamini, Schmidt, and Yafeev again reduces the problem to proving that the Vey height is discriminant negligible. And Jacob and co-authors established this in 2021 by defining an almost canonical height on the special points. And in each case, this arithmetic ingredient completed the proof of the André Oort conjecture. Now, Hodge theory vastly generalizes the picture of Shimura varieties. Over a family of algebraic varieties, integrating suitable differential forms, one gets the period map, taking a variety in the family to its periods, which are some numbers that move in the family. The Shimura variety case is a special case in which the image of this map, modulo its monodromy, is itself an algebraic variety. So here I will be even more brief describing Jacob's fundamental contributions, and but I can recommend that that people go to the talks by Ben Baker and by Jacob at this Congress to hear more. So with collaborators, Jacob proved definability of period maps of variations of mixed Hodge structures. And here definability means in an O-minimal structure. This establishes a strong tameness of these maps that can be powerfully exploited. In particular, to reprove the fundamental theorem of Catani, Deligne, and Kaplan, establishing the algebraicity of the Hodge locus, and to develop an O-minimal gaga, paralleling the classic gaga of Serre, and further applying these tools to fundamental advances, in particular proving a 50-year-old foundational conjecture of Griffith's. So Jacob has made several other deep contributions in a range of areas that I won't go through. And at this point, just say, congratulations, Jacob, on your wonderful results. Okay, thank you.
Okay, so that's it. As you can see, it's very technical. Don't worry if you didn't understand. I also didn't understand because, as I said at the beginning, this is not my corners of mathematics. But the prerequisite stuff that I shared before, just in case you are just joining or joined late, let me share that again. If you, in parallel to watching and then going back to referencing to those to these materials that I will share now with you, you should be able to follow something. Okay, so definitely you need this. Okay, you need to understand. This book is a great reference. I actually used it. By the way, I watched this talk before. In fact, I watched it more than once, and I was referencing to these resources, going back to myself to try to get something, picture something. Okay, so this is a reference one. The second reference is this one, where you learn more about an introduction to Diophantine geometry. In particular, you get introduction to stuff like abelian varieties, rational points on algebraic variety, and all these stuff that are the basic stuff. And then this is also very good for complex abelian variety. And finally, this one on moduli spaces or moduli spaces, however you decide to pronounce it. I was saying before, just in case you joined late, you probably been you have experience with moduli spaces without knowing, because manifolds, they have this thing. They are moduli spaces. You can get moduli spaces out of them. So yeah, so go and check these resources. Actually, there is another one. This one about this framework, that Jacob used in his work. This thing, I think he called it o-minimality. So this resource here will give you that, and then finally, this is a gold mine, by the way, not just with the Jacob stuff. I mentioned this before at the beginning, just in case again you joined late. In my student days, more than 20 years ago, I used to come to this site. This is actually the first site where I downloaded a PDF on I downloaded a PDF on Galois theory. So J.S. Mill's website is a gold mine, really. It's been around for decades. Okay, so go and check these resources, and then take your time to watch the talk and pause and go back to the resources, to whatever the concept that he's talking about, and take notes and see whether you can picture something. If not, well, you have the books anyway, the resources, as a reference in case you want to go and take a look. So yeah, so let me share here. I will go to the chat in a minute, but before that, any questions? Seems I disappeared. as I said, don't worry if you don't understand anything. This is really, his field is very abstract. It's very, very, very specialized. And it also is like multifaceted. With different fields of mathematics, coming together. So, and as I was saying, modern mathematics is very specialized. Even between mathematicians, there is this barrier of language. You don't expect a mathematician in one field to really understand another mathematician. I also mentioned the Langlands program, this thing of trying to create a framework to enable different fields of mathematics to understand each other, to connect with each other and make the mathematicians understand each other. Okay. So I hope you enjoyed that, and don't worry if you didn't understand anything. I also, before I got these resources together, I didn't understand much really. Well, I knew what a variety is and these things, but at a superficial level. As I said, these corners of mathematics are not my my thing. Okay, so the other thing I want to comment, from my understanding, basically, the main reason why he was awarded, or at least one of the contributing factors, is his work on the André Oort conjecture. So, in a nutshell, I think we can say that the conjecture says that if I recall well, if a subvariety of a Shimura variety contains a Zarinsky dense collection of special points, then that subvariety must itself be a special subvariety with some sort of extra arithmetic and geometric information or structure. Okay, so this is one part. The other part is in the contribution for proving strong lower bounds for the what the speaker was just mentioning, the Galois orbits of special points in moduli spaces of abelian varieties. So yeah, and this brings me to the thing about honoring Grothendieck, because a lot of the thing that people like Jacob Tsimerman, they are working on, they are like legacy of past mathematicians, including Grothendieck in particular. I won't be sharing that much about the life of Grothendieck and these things, because I think we have a post here on our Substack by my colleague Jack Novak about a study of a Grothendieck, and there is a section there a bit about his life, early life, and then the late stages, and also his philosophy as well a bit. Yeah, so go and read about it a bit on the personal side of Grothendieck. But what I could understand, the pillar, like the key to like Tsimerman's work, first of all, let's see who is Grothendieck. Okay, Grothendieck basically helped reshape algebraic geometry by developing a much more like in the case of variety, a much more general framework for varieties, and stuff like also like cohomology and the relationship, this type of stuff. Okay, and one of the things that came to Grothendieck from Grothendieck at the time was this thing of this Grothendieck this thing called Grothendieck period. This guy, this work, which basically to do with the variety and transcendental numbers. That's why you say numbers. Algebraic relations between this period should be explained by algebraic relations coming from the variety itself. Okay, so this is also one of the things that connects, I suppose, Tsimerman's work in Hodge theory with periodic maps, for instance. Okay, so that's the thing. So this is just to say the reason I'm mentioning this is because very often people think mathematicians' work just come out of years. Mathematics is built on top of bodies of work, sometimes decades before or even centuries before. Okay, and in this case, I'm highlighting Grothendieck, because he's one of the greatest, and he also he also the field of algebraic. Okay. Trying to connect. I see a network thing. I hope. Don't worry if you didn't catch the other thing that I was saying. The network is playing with me. I'm sorry for this. But the HD recording will have everything, because everything is recorded locally on mine. So you shouldn't miss any word if the internet catch. Yeah. So anyway, in respect to Grothendieck, what I was just saying, maybe you might want to look at this paper by Grothendieck. Look at it. I will also add it in the thing in the notes for the recording. And a second paper also relevant, pertinent to what I was just saying about connection, the influence of work of past mathematicians like Grothendieck in Tsimerman's work, is this second paper. Yeah, I'll give you 10 seconds for you to take a screenshot. But again, if you can't, just wait for us to put the recordings, and I will add all this on the thing, including I will also add the reference resources that I gave you on, algebraic geometry, on Diophantine geometry, all these other things, or moduli spaces, all these resources that you can take and study in trying to make sense of his work. I will gather all that and on the thing on our Substack once we post the recording for this. So that's it, really. The other thing I suppose I would mention is Jacob Tsimerman has recently joined OpenAI. So this is Mark Chen. I think he's one of their OpenAI's chief scientists or something. I'm not sure exactly what his position, but he's one of the top people on the research team. So he's welcoming Jacob Tsimerman to OpenAI. It seems like Jacob Tsimerman has some interest in AI safety. So yeah, so OpenAI recruited him. I have a mixed feeling about this, but let me start with the positive. The positive is, it's always great to have mathematicians, go to these labs, that traditionally are dominated by, just pure computer science or software people. So, having mathematicians help them, people of Jacob Tsimerman's caliber could possibly, help them make some inroads in safety. So yeah, so that's the positive side. The other side, I think Jacob has, he's very young. I don't know how long. First of all, I don't think he has left academia. I think he's going to AI. But what I'm saying is that it's a shame that his mathematical work by going and working with us. But at the end of the day, it's a personal decision. He decided that this, of course, one has to respect it. But on the positive side, as I was saying, I think it's always good to have attention on these. On the other side, the time he's spending in anything on at Open Lab, maybe he could be creating another breakthrough. So yeah, so it's a mixed feeling from me. In a way, I'm happy that he joined OpenAI to work on safety, right? We all worry about model safety. On the other hand, I'm also worried, the time he's spending on the OpenAI, not working on mathematics, maybe, what have you lost, with using his talent, to try to, maybe solve another important problem in mathematics. Yeah, so that's basically my thing. But yeah, it's a personal decision to be made. He's still young, and as I said before, he hasn't left. I don't think he left. I think he's on sabbatical to join OpenAI. Maybe he will come back again to academia and start doing maths. Or maybe he does the maths from OpenAI. Who knows? But yeah, so that's, I thought you might want to know that he joined OpenAI to go and work on AI safety. Okay, so that's it really, and again, I apologize because the other mathematician who's actually algebraic, works in arithmetic algebraic geometry that I had in mind, we agreed that he would show up to walk you through Jacob Tsimerman's job. Unfortunately, because of family, kids thing, health related stuff, he has to bail out, but he will come back and do a webinar for us. So, but I hope you enjoyed my improvisation. I myself have been trying, for the past 2 weeks to try to understand something about his work. As I said, the corners of mathematics of Jacob Tsimerman is not really where I am. So yeah, but I hope also you like the resources that I share with you to do the same as me, cross-reference, to go and refresh in different topics that you need to try to put the pieces together about his work. Yeah, it takes a lot of time, so you really need the time and patience to do this. So don't do it if it's just the time, because you will feel frustrated and you might just give up. Okay. On the other hand, if you get resources, maybe you might find the fields, the topics that he's working on interesting enough mathematically. Maybe you yourself, you might want to pursue it. So yeah. Any questions? I suppose it's been like a very long session. Any comments? I don't blame you, because this is very, 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 very abstract, really, his work, So you might not have any questions at the moment. I actually had some technical questions that I wanted to ask our friends, but it doesn't worth asking it because, we wouldn't know the answer, but he would. So yeah, so maybe we save that, or even save your questions if you don't have any questions, for the webinar that our friend from arithmetic algebraic geometry will do for walking us through Jacob Tsimerman's work. Okay. Final opportunity to make any comment or yeah. One thing definitely as a motivation for you, as I was saying, you've been working with moduli spaces without knowing, if you deal with smooth manifolds and these things. Okay, so take that for comfort. Okay, yeah, I see someone saying they will be exploring moduli spaces. Okay, that's good. They never heard of it before. Well, I'm glad. This is one of the reasons. Yeah, so this is one of the reasons we hold these sessions. You don't have to. The takeaway doesn't have to be a massive list. If you go with at least something interesting, like in your case, you never heard of moduli spaces, and you didn't know that manifolds, there are examples, that you can have moduli spaces with manifolds. Then yeah, that's great. It means that you can go from the perspective of manifolds to try to see what moduli spaces give you. Okay, so this is already a positive thing. Thank you for sharing this. Okay, well, in that case, thank you so much. And yeah, and I'm sorry again, we couldn't have the original guest that was meant to be on the session with me, who is an actual expert on, or at least closer to the fields where Jacob Tsimerman sits. So yeah, follow us on LinkedIn, subscribe to our Substack for the next field medals coverage. I think the next one will probably, I'm not sure, I think it will be John Pardon. Yeah, so I see you for that session. Until then, thank you for showing up and spending this time, and sorry for the technical issues that we faced before. So yeah, I'll see you next time. Thank you again for joining.